Artificial intelligence is, well, it's just exploding, right? Every single day, these models are getting smarter, more capable, and just astronomically bigger. But all this incredible growth is actually creating a kind of hidden crisis. See, the very hardware that powers AI is being pushed to its absolute limits, and we're about to slam right into a fundamental barrier, the memory wall. So, the big question is, how do we break through it? In this explainer, we're going to first unpack the problem itself, then dive into this really powerful 4-layer solution. We'll look at how engineers are making models smaller, then faster, and ultimately a whole lot smarter right from the ground up. Okay, so what is this crisis, really? Well, at its core, it's a speed problem, a massive, massive gap that's opening up between how fast AI software is evolving and the hardware that's just struggling to keep up. And here it is in just stark numbers. The size of these AI models is exploding. We're talking 410 times bigger every 2 years. But the GPU memory they need, that's only doubling in the same amount of time. I mean, you can do the math. That is completely unsustainable. This crazy gap has a name. It's called the memory wall. What it really means is that the bottleneck isn't the raw processing power anymore. It's the traffic jam of data trying to get to the processor. And if we can't find a way through this wall, all this incredible AI progress could just grind to a halt. So how in the world do we tear this wall down? Well, there's no single silver bullet. The solution is actually a really clever full-stack attack, a 4-layer strategy that optimizes everything from the AI model itself all the way down to the hardware. Yeah, this whole full-stack idea is absolutely key. It's not about finding one little magic fix. It's about optimizing the entire system all at once. You know, it really is like tuning a Formula One car. You can't just have a powerful engine. You have to optimize the fuel, the aerodynamics, the tires, the whole shebang. And here are those 4 layers we're going to talk about. We'll start at the bottom with making the models themselves smaller. Then we'll move up to the methods for getting answers out of them faster. After that, we'll look at building smarter blueprints or architectures from the very beginning. And finally, we'll rethink the actual applications that use these models. So let's start with layer 1. All right, layer 1, model optimization. The big question here is a pretty tricky one. How do you shrink a massive AI model without making it, well, dumber? A huge technique here is something called quantization. Okay, imagine an artist palette with literally millions of different shades of color. Quantization is like cleverly reducing that down to maybe just a few thousand essential shades. You still get a beautiful picture, but it takes up way, way less space. For AI, this means turning these super precise numbers into simpler ones, which saves a ton of memory and speeds everything up. And this is where a technique called I-BERT gets really, really clever. If you look at those messy loops on the left and in the middle, you can see how older methods wasted tons of energy converting numbers back and forth. But then look at the I-BERT flow on the far right. It's a straight line. By staying entirely in that simple integer world, it just eliminates all that wasted effort. It's incredibly efficient. And the result of that efficiency? It's just stunning. This integer-only approach gives I-BERT a massive performance boost. We're talking about making models run up to 3.5 times faster. That is a huge leap, and it's from just one optimization. Okay, so we've made the model smaller. Now let's move up to layer 2 and make it faster. This is all about improving what we call inference, which is just the process of actually getting an answer from the model and doing it at top speed. You see, a huge speed bump for a lot of language models is how they actually generate text. They basically work like a slow assembly line, producing just one single word at a time. This step-by-step process is a major, major performance bottleneck. But what if you could break out of that one word at a time trap? Well, there's this brilliant solution called the Big Little Decoder, or BUILD, and it does exactly that. Think of it like this. You've got a fast junior writer just churning out a draft, and then a brilliant senior editor comes in and reviews and perfects it in entire paragraphs at once. The small model generates, the large model refines, and the whole thing gets a massive speed boost. So what's the bottom line? This tag team approach can effectively double the speed of text generation. It's really the best of both worlds. You get the powerhouse quality of the big model, but you get it at the blistering pace of the small one. This brings us to the final 2 layers of our stack, and this is where the focus really shifts. So far, we've been optimizing models that already exist. But what if we could build them smarter, right from the very beginning?
This is about fundamentally changing the architecture and the applications themselves.
And that's where layers 3 and 4 come in. So at the architecture level, this means designing models from the ground up for specific jobs, like speech, making them just inherently more efficient. And then at the application level, it's about being smarter with how we even ask for things. Instead of one long command, a system can break it down into a bunch of smaller jobs that can all run at the same time, in parallel. And this visual just makes the difference crystal clear. On the left, you've got the old way. It's a slow, sequential domino effect where each task has to wait for the last one to finish. But on the right is the new parallel approach. It's like a multi-lane highway where all these different tasks can run at the exact same time. This is an absolute game changer for speed. So, when you combine all 4 layers of this full-stack strategy, you've got smaller models, faster inference, smarter architectures, and parallel applications. The results are truly transformative. AI becomes dramatically faster, cheaper, and way more accessible. It's what makes it practical to run powerful AI on everything from these huge data centers right down to the phone that's in your pocket. And that leaves us with one last but really crucial question. For years, the AI race has been all about scale, right? Who can build the biggest model? But as we're all slamming into this memory wall, maybe the defining challenge for the next era of AI isn't who can build the biggest one, but who can build the smartest, most efficient one.